A hurricane tears through the Gulf Coast, and the Florida communication grid goes dark. Cell towers drop offline, entire counties are isolated, and emergency responders lose contact with the hospitals they are desperate to reach. As the storm clears, the immediate engineering challenge becomes a brutal exercise in triage, identifying the exact 3 or 4 repairs that will bring the majority of the isolated clusters back online. Looking at the shattered grid, the most critical nodes to fix are rarely the largest towers or the ones with the most visible damage, leaving response teams to guess at a sequence where intuition almost always fails. That same hidden vulnerability exists inside the everyday systems we rely on, waiting to be exposed the moment we view them purely as mathematical networks. In a standard spreadsheet, the massive, high-traffic downtown hub looks like the system's most vital asset, the focal point of any traditional maintenance plan.
Yet the actual structural risk lies miles away, in a quiet station handling a fraction of the ridership, a solitary bridge holding 2 halves of the map together, where a single failure cleanly snaps the entire network in 2. We see this same blind spot repeated when moving from physical transit to the tiered logistics webs that route the world's materials. An insignificant peripheral supplier flickers and vanishes, a minor event that traditional risk analysis often ignores as a rounding error. But because of invisible dependencies woven deep into the system, that minor failure propagates upward, choking off supply lines until a massive cluster of retail endpoints goes completely dark without ever sustaining a direct hit. Under extreme pressure, these hidden architectures dictate exactly where a system will buckle, especially when millions of people are trying to escape a storm path. Basic intuition leads engineers to reinforce the widest, most prominent highways, assuming the highest capacity will naturally handle the highest surge in traffic. But the outward flow ultimately jams miles away at a minor intersection that nobody thought to map, paralyzing the evacuation and leaving the reinforced highway completely empty. Treating interconnected infrastructure like a collection of independent parts is a systemic risk that intuition alone cannot solve. In SISON 5470, Network Science and Applications for Systems Engineering at Cornell University, you spend 3 intensive weeks mapping real-world systems to measure the structural weaknesses that standard analytics leave behind. Taught by Dr. Tim Fraser, this course gives you the computational tools to look at a tangled web of dependencies, pick up a sketchpad, and finally trace the true architecture of failure.